All right, welcome. Today we'll be deriving the equations of constant acceleration. So they're sometimes called the big four in physics, the big four equations of constant acceleration. And to begin, we're going to consider an object whose velocity changes. So acceleration is a change in velocity, speeding up or slowing down. So we're going to consider velocity measured in meters per second, plotted against time this way. So this is called a velocity time graph. Velocity in meters per second, time in seconds. And so we'll have an object that starts with some non-zero speed. So 0 would be here, right? So 0 seconds of time, 0 meters per second of velocity at the origin, so a true 0. And so we're going to say, here's an object who starts at a speed of this and increases uniformly to a final speed, here. So let's say the final speed is v sub f. The initial speed was v sub I, and we reach that after a time t. So an object starts at speed v, accelerates to speed v sub f over time t, right, from 0 to t. Don't worry about that. The two things that you can do with graphs are find the area underneath the curve, and that's an idea in calculus known as an integral. And then we can find the gradient, the slope of the line, and that's an idea in calculus known as a derivative. And so derivatives and integrals are the two sort of big ideas in calculus. And we don't need calculus to solve these because it's just a straight line, so we can sort of just use geometry to solve for like the area underneath this. But if it's sort of curved line, then you need calculus, okay? So with this, uniform increase in velocity, we should be able to get by with just some algebra. If there were no acceleration, okay, then the object were just traveling sort of at an initial velocity like this, then we can kind of think about, well, how much distance is covered if something just travels at a speed, stays at that speed for a certain amount of time. So this is like saying, if I want to go to Miami, which is 200 miles away, and I travel 200 miles per hour, then I will be there in 1 hour, well before curfew, okay? But going 200 miles an hour, you're going to make it all the way to Miami before you get, pulled over. So, but that's the idea. It's like the distance traveled is just the velocity times the time. Okay, so that's the area underneath this curve. The area underneath the curve gives distance traveled. If you think about length times width, that would be the area of this rectangle, and the length would be in meters per second, the width would be in seconds, and so the seconds would cancel, and we'd be in meters of distance traveled, right? So the units kind of give us a clue as to what we're solving for. So the area underneath this curve will give us the distance, and we can kind of think about it as there's some distance that's covered because we were already going at this speed, and there's extra distance that's covered because we're actually picking up speed, right? We're increasing our speed. An example that I sort of like to use to make this more familiar would be like you're speeding up to merge onto the interstate. So you're going like maybe 50 miles an hour on highway, and then you speed up to 70 miles an hour, so you're going at the speed of the interstate highway. Well, as an engineer, you kind of want to know how much road, how much ramp do you need to build to give cars adequate, distance so that they can bring their car up to speed, keeping in mind how typical accelerations are for cars. So the area underneath this curve gives us the distance, and the slope gives us the acceleration. If we think about the rise over the run, the rise would be in meters per second. The run would be in seconds, and we have meters per second or meters per second squared. And that's actually the definition of acceleration, is the change in velocity per time. So the rise from here to here would be the difference between VF and VI, right? The difference between these values is the rise, or it's like taking the Y coordinates, the difference in the Y coordinates, VF minus VI, the change in velocity over time, right? So that happens over this time. That's like the run. So rise over run, that's the slope. The slope of a velocity time graph gives acceleration. This is like the definition of acceleration. We get our first equation, the first one that you see on the other chalkboard, by getting rid of the negative sign and getting rid of the fraction. So multiply both sides by t, and we have AT equal to VF minus VI. And then we get rid of the negative VI by adding it to both sides. So we get our first equation that solves for the final velocity. It's whatever the initial velocity was plus the acceleration times time. By multiplying acceleration and time, you get like the extra velocity you're picking up that gets added into your initial velocity, so you can record what your final velocity is. It's like saying if I'm going at an initial speed of 0, let's make it easy, 0, but I accelerate at 9.8 meters per second every second for 1 second, then my final velocity will be 9.8. So this is like what gravity does. Remember, that's why we put it on the board over there. For these problems, for our rocket science, the acceleration is due to gravity. It's the constant accelerator. We can just call that lowercase g, local g, and on Earth, we know it has a value of 9.8 meters per second squared. So this will be known. Like gravity will be the thing that's slowing down our payload, speeding it back up. We're going to do this midterm here on Earth, okay, in this gravity field that we're all experiencing right now. So here I've just added VI to both sides to get this equation 1. We can use this to solve for the initial velocity of our rocket. So we launch our rocket upwards, it travels some distance up, it falls back down, it reaches a maximum height, we can call it h, or the altitude. Don't call it a for altitude because, you know, a for acceleration, so it's like we gotta make it all clear here. And we know that gravity opposes this initial velocity. So we're launching upwards, and now we have to sort of consider the vector nature of this, that this is going to be a positive velocity, and gravity opposes it, so it's negative relative to them. Like if we launch, if we're calling up positive, then gravity is negative, okay, because it's acting down. It doesn't matter as like the physicist, you know, examining a situation. It's up to the physicist to decide what direction is positive or negative. The important thing is that they oppose each other. Like when vectors are going in different directions, one is negative relative to the other one. It's arbitrary. Like, you know, I can call this direction negative and then make this positive. Down could be positive. It doesn't really matter. As long as you keep track of, you know, the opposition of the vectors. So that's equation 1, and we would use it to solve for this initial velocity because we know something about the motion of the object right at this point. Okay, gravity slows down our tennis ball to a temporary speed, a temporary final speed of 0 meters per second. It has to reach a speed of 0 before it can sort of turn around and go back the other way. So we want to know this. We want to know how fast we can launch our rockets. We know that we're going to collect data in the field of the total time airborne. So we're going to start our stopwatch right after launch, let it go up, and then let it fall all the way down. Now, we really want to know the time to get to here. So we take the total time airborne and we just divide it by 2. It's easier to sort of judge when the ball hits the ground and stop your stopwatch than to judge when is the ball at the top of its flight up there. You could directly just measure the time to max height. But I tend to think that there's more uncertainty in that than just letting it go all the way up, all the way down, saying, okay, I've got the total time airborne. The time airborne t divided by 2 gives me lowercase t, the time to max height. I really need to know what that is, and I have to collect that data myself out in the field. All right. You'll notice when we derive these equations that we're always relating 4 variables in any given equation, but there's 5 total variables that are sort of involved in these equations. This equation does not include displacement or distance, right? So distance traveled is not sort of included in that first one. To get to the other equations, we're going to consider sort of the other important idea that I mentioned, which is the area underneath this curve gives us the distance traveled. Again, you can just kind of think about like length times width, so meters per second times seconds. Seconds cancels, we get meters of displacement. So we'll start with the distance traveled, d, is equal to the area underneath this curve. Now, because it's a straight line, we could, you know, like if you knew the area of a trapezoid, this is technically a trapezoid, right? And we could, you know, plug that in, but we'll break it down into a rectangle and a triangle. So we don't need calculus to integrate underneath this curve. We just say, hey, I know geometry, I know how to calculate the area of a rectangle. Length, which would be VI, times width, which would be T. So we have VI times T. This is just the distance traveled without accelerating. Like I said, this is just like I'm going 200 miles per hour, and if I can travel that fast for 1 hour, I'm going to be 200 miles away. You know, if I can, right? That's kind of just well above the speed limit. So this part of the figure, the distance is VIT. This one up here, we've got a triangle, and we know that the area of a triangle is 1/2 base times height. The base, okay, is this sort of side right here, and it's equal to VF minus VI, the same sort of rise in a rise over run calculation, right? Like this value here is VF minus VI. But I wrote this here for a reason. It's equal to, look, AT. So the base here is really AT, all right? So we know that the area of this triangle right here is going to be 1/2 the base, AT, times the height, which is still T. So 1/2 AT times another T is 1/2 AT squared. And so that's another piece of the distance. So the total distance that's covered when an object accelerates from some initial speed to some final speed over time T is equal to VIT, that's the distance traveled by virtue of the fact that it was already going at this non-zero speed, plus the added displacement, this term, which is going to be sort of equal to the area of this triangle. That's the extra sort of distance that's covered because we're speeding up, right? Like we're not just going 200, or we're not just going 55. We're speeding up from 55 to 70. And so we know we're going to cover this distance just because we're going 55 to start out with, but we get this extra distance because we're not going 55, we're going 55, 56, 57, all the way up to 70. And so this term, which also gives a distance, adds to the distance that you would cover, which is represented by the area here, and give you the total distance. If you just think about the units of this term, meters per second squared of acceleration times seconds squared of time, so the seconds squared cancel, we're just left with meters. So this term gives you meters of distance, this term gives you meters of distance. The 2 meters of distance together give you the total sort of distance traveled. So there you go. Note that this equation lacked distance. This equation lacks final velocity. Final velocity doesn't show up in this equation. We can be clever now, and we could say, even though we started at speed VI and ended at speed VF, couldn't we just sort of say that we were going at average speed of like this dashed line here? So even though we started a bit slower and ended a bit faster, we could say on average we were just going this fast. We were just going VF plus VI over 2, right? So it'd be like their sum divided by 2, that's their average, right? So you add 2 things and divide by that, you get it. So the value of this dashed line right here is the average of these two, VF plus VI over 2. And then we can do the same thing. We know that the area of this white box now is going to be the distance traveled, okay? So rather than dealing with the acceleration, we just treat it like, oh, just constant velocity, just like we have here. So it's just going to be length times width, okay? So another equation for distance, because it's the area underneath. And it's going to be the length, which is this value. And I'm going to rewrite it like this, okay? 1/2 VI plus VF. That's the same thing as VI plus VF over 2, right? We just pull that 1/2 out front. So that's the length times the width is T, and there you go. So here's an equation of motion. It's the third one on that list over there. And this is where it comes from. It comes from considering that the area underneath the velocity time graph gives displacement, and that we can actually average our change in velocity to like some value that's in the middle of both of them. So the area of this square equals the area of this trapezoid, right? It's the same distance. Here we sort of like, we're adding in this extra bit, right, in the white square, but we're subtracting out this bit, right? We're not accounting for that. And so the area of that and that are the same, even though it doesn't look like it by the way I do the figure. It's not the scale, I'm just sort of doing it by hand. So there's equation 3. Note that it doesn't contain acceleration because we sort of said, well, let's not consider it as acceleration. Let's just consider it as like this constant velocity, and it works. You know, you'll find that that gives you the same answer. So that's kind of nice. To get our final equation of motion, it's one that doesn't include time. So note, again, every equation omits one of the 5 variables. In order to solve something, like we're going to solve for our initial velocity, we need to know 3 of them. We need to know 3 of these 4 in order to solve it. So say like, okay, I want to know VI. I knew it reached a final speed temporarily of 0. I can measure the time airborne and therefore get this value T. And I know that I'm on Earth with acceleration due to gravity equal to 9.8. So I do have 3 of these 4 known, so I can use it to solve for my unknown. right? So we're going to sort of think about it when we go out for our midterm that the initial velocity is just going to be equal to, well, let's do it formally. The final velocity equals the initial velocity plus AT. In general, we know the final velocity is 0. The initial velocity is what we want to know. We know that gravity is negative. If this is a positive, then gravity is negative relative to it. Times whatever time we get, half of our time airborne. So then we just add this to both sides, and then we can see that the initial velocity is just equal to 9.8 times t. So that's how you solve for how fast the rocket went. It's just however long it took to sort of fall from this, or to go up to that height, this is the same value, times the acceleration due to gravity. That's how we get our initial velocity. All right, so here we're going to rewrite this equation, the equation of acceleration, in terms of t. Bless you. So that's going to be t equals vf minus vi over a. If I multiply those sides by t, ta, it's this actually. And then if I divide those sides by a, I get this. T equals, this over a. So that's what t is. Remember that. That's what t is. Now I'm going to rewrite this guy. Distance equals, just like I could go from like this form to this form, I'll go back again. All right, so I'm going to rewrite it like this. Vi plus vf over 2. The distance equals that times time. Now, because I want an equation that doesn't include this variable, I'm going to substitute for it. That's where this comes into play. So it's like, it's this times t, right? Well, what's t? T is that. So I'm going to multiply this by vf minus vi over a. So like, well, why would you do that? That just looks a lot worse. Well, this is that's what it's equal to. Nothing we can do about it. So in order to multiply these two fractions, it's easier to multiply fractions than to add them. Remember, we don't need a common denominator. We just say numerator times numerator gives me my new numerator. Denominator times denominator gives me my new denominator. So I will do, I guess it doesn't matter. I'll do the denominator. Okay, you guys do the numerator. 2a, there you go. All right, you're welcome. And now you guys get the, the numerator. No worries. You took the easy one. We wanted the denominator. We wanted to multiply 2 times a and get 2a. Everybody know how to multiply these binomials up here? Anybody know how to do that? Anybody like thinking of foiling this? Foil? Huh? Remember, first, outside, inside, last. It's a way to distribute binomials. So I'm sure if you sort of recall back to your algebra days, you go, oh yeah, FOIL. We FOIL binomials. That's how we multiply. It's really just distributed. So we're going to have VI times VF. VI, VF. That's the first. Then we do the outside. So VI times negative VI is negative VI squared. Then we got the inside. So these two VFs multiplied by each other is VF squared. And then we got negative VI, VF. So minus VI, VF. And so VI, VF cancels, right? Or VI, VF minus VI, VF is 0. 0 plus the rest of that is just the rest of that. And so we'll rewrite this over here like D equals negative VI squared plus VF squared over 2a. And just like up here, we didn't like the fraction, we didn't like the negative sign, so we multiplied by t and then added it. We got this. We do the same thing to that one. So we multiply both sides by 2a, and we get 2ab equals negative vi squared plus vf squared, and then we don't want a negative, so we're going to add that to this side of the equation, and we will get our final equation. Vf squared all by itself is equal to positive vi squared on the other side of the equation plus 2ad. So this is a helpful equation if we don't care about time. It was just like something is speeding up from this speed to this speed. It's going to cover a certain distance because of a certain value of acceleration. And this is how they are related. All right, that's what the numbers don't lie. That's what the mathematics indicate. So the final speed squared is equal to the initial speed squared plus twice the acceleration times the distance traveled. Like an engineer who's designing a road that's like, okay, you're going from 55 to 70. Cars can accelerate, this much. I'll use this equation to solve for how long I should build a road, because I don't care how long it takes people to get up to speed. There could be traffic, I just need to make sure that I give them enough distance to bring themselves up to speed. The time maybe doesn't even really matter there. So you'll see in the 4 equations, 1, 2, 3, 4, the big 4, that again, we're relating 4 of the 5 variables, and to solve for anything, we need to know 3 of them. So for our midterm, one conclusion we reach is the initial velocity, because we know what the acceleration is on Earth. We know that gravity is going to stop our payload, our tennis ball. No one's going to sort of launch into outer space and achieve orbit probably, so gravity will slow it down before it speeds it back up in the opposite direction. So we know it must have been temporarily 0, right at the point that we want to know the height too, right? So that's convenient. And then time, we've got to measure. Like, we got to collect some kind of data. So by simply measuring the time airborne, you can deduce how fast you threw a ball. And it should just make intuitive sense that, like, the longer it's airborne, if I throw a ball up in the air and it takes like a whole bunch of time for it to fall down, I must have thrown it pretty fast, right? The less time it takes to fall, the slower I threw it. And moreover, that's not just like a nice relationship we can hold up in our mind. We can quantify it very clearly, and we can predict exactly how fast we threw it if we've measured the time accurately. To get the height, I told you before, like computationally, here's a nice equation for you. 1/2 gt squared, that's how you solve for height. And today's lesson is really about seeing where does this come from. Like, you can just trust me as your, science teacher that I tell you, hey, you want to know how high up something is? Drop it, time it, square that time, multiply it by 9.8, multiply it by 1/2, that's how high up you are. Like, you drop a rock from a tall bridge and it takes 3 seconds to hit the ground, 3 squared is 9, 9 times 10 is 90, 1/2 of 90 is 45. That's about 45 meters tall. If you drop something and it takes 3 seconds to fall, you're about 45 meters up, okay? That's like, what, 150 feet. Okay, you gotta be pretty high up to let something fall for 3 seconds. Because gravity accelerates things so much here on Earth, right? Every second something falls, it picks up 10 meters per second, about 23 miles per hour speed. So this equation is actually this one, all right? It's, the height is the distance, but we're considering, like, if I just dropped a tennis ball from its maximum height, it would take this time to fall down. So if I just sort of considered the motion of an object, like a ball starts here, I drop it, it falls down, what's the initial velocity of something you drop? Exactly, no one said anything because you guys know that it's 0. So this term goes away. If the initial velocity is 0, it doesn't matter how much time, right? 0 times whatever is 0. And you just get this simplification of the distance, the displacement vector, the height in our case, is equal to 1/2 the acceleration times time squared. So instead of just calling it d for some sort of general distance, we call it h because it's height. Again, don't call it a for altitude. A is already taken. Okay, it's acceleration. Call it h for height. And then it's like this g is the same as this a, like a, the acceleration due to gravity, or just local g, we call it. And so that's where this comes from. It's just sort of plugging in what we know into this equation. So it'd be, okay, the height is equal to, well, this is 0, right? The initial velocity of something that just falls from there is 0, plus 1/2 9.8 times the time squared. Okay, and then that's how we can solve for the height. So once again, this will be something we're already going to know. We measure the time airborne, cut it in half, and we got t, times it by itself, times it by 9.8, times it by 1/2, and you solve for the height. Because g is in meters per second squared, when you multiply it by seconds squared of time, you're getting the height in meters. As a final step, remember to multiply 3.28 feet per meter to get your answer in feet. So one conclusion is going to be the initial velocity of your launch in meters per second, again, because 9.8 is meters per second squared, so times seconds of time. One of those seconds cancels, and we get meters per second of velocity. Multiply it by 2.23, and that will convert it into miles per hour. This is cool if you're like, ever have to babysit, somebody, and you could take them outside and say, hey, throw this in the air, I'm going to time you, I know enough physics, I'm going to tell you. They're like, we don't need to go to the the batting cages to like, throw a ball, to get a speedometer, see how fast we can throw a ball. We'll just know our physics. Just throw it up in the air, let gravity act on it. I know enough physics to tell you how fast you threw that ball and how high up it went. And that's all you need, just a stopwatch. Find that, you know that gravity, now you've got this physics. And if any of this was unclear, just go ahead and hit that pause button, rewind it a bit, and watch it again. All right, we'll see you next time.